So my name is Bill Fisher. I'm here today with Jing Chen, and we both work at Facebook. We're software engineers there. And we're here to talk about Flux and React and how we use a application architecture that has a single direction data flow, and how that cleans up a lot of our code. We've built things with Flux ranging from very small little widgets to some of the largest web applications that we know of, things that are revenue critical at Facebook. And so Flux has scaled with us to do pretty much anything that we throw at it, and has done it really well. So we wanted to share some of that with you. There's an available speaker deck if you would like to download that or follow along online. And there's also a new GitHub repo for Flux that we are open sourcing today. So there's also, I know there's the hashtags, and these hashtags are great to share on Facebook or maybe some other social network that you know about. So these are recommended just to keep everybody in sync on the back channel. So without further ado, let's do an overview of what we're going to talk about. First, we'll talk about Flux and React and sort of what they are on a general level. And then Jing will take us on a deep dive into stores. Stores are the data layer in Flux, and we'll talk about how they work. I'll go over an example application, and then we'll wind it up at the end with some advanced concepts and talk about where Flux is headed in the future. So without further ado, I'd like to introduce Jing Chen, the original author of Flux.
Thanks, Phil. All right, so a couple of you guys might have seen our post on the React blog back in April. Show of hands, how many of you guys are familiar with Flux and React or have heard of it already? Okay, pretty good number. Great, so there's a URL here if you guys want to check it out afterward, but that was sort of our very early introduction to Flux, and we also had an introductory video on there. But just to start with a little bit of background, with Flux, we think of it as a single directional data flow architecture. And what we found is that if we constrain the structure of your app, starting from the very beginning, then as your app scales up, it doesn't explode in complexity. We can sort of restrain that a little bit by sort of keeping to the same structure and making that easier for the developer to keep in mind. And then another key part is that we use stores instead of models. And Bill's going to dive into that a little bit more with the example app. It seems like a lot of you have heard of React, but just to go through that, React is Facebook's open source JavaScript rendering library, and we found that Flux and React work really well together. We don't say that you have to use them together. The only requirement for Flux is that when you want to render something, you can render everything as if it's from a fresh state. Because Flux does not sort of give updates as in, here's what actually changed. It just says, hey, something changed. So that's really the only requirement. But what React does is it conceptually allows you to think of your UI as re-rendering on every single change. And that doesn't seem very performant, but the main reason it is that it's not actually re-rendering under the hood. It sort of provides you the interface to say, given the state A, here's how to render that. Given a state B, here's the different rendering layout of your view. And then it sort of takes the virtual DOM representation of both of them, does a diff, and applies only the changes that have actually happened. So that's how React sort of keeps it performant. It conceptually is a re-render every time, but under the hood, it's sort of optimizing things for you. That sort of just leads to a simpler mental model. If you can just think of everything as very declarative, given a state A, how do you render that? That makes for a very simple mental model. And Flux and React are both, all about keeping a simple mental model. Okay, so let's talk a little bit about stores. We've gotten a lot of questions about this, so that's why we've sort of decided to talk about stores as our main part. We think of stores as sort of fat models. It contains all of the data pertaining to a logical domain. So in the example app for chat, the one store would be the messages store, and it would contain all of the messages that we know about on the client, not just a single one. It also includes all of the application logic for that logical domain. So I'll explain a little bit about what that means. But the very beginning is that it will set up to register with a dispatcher. In our system, a dispatcher is just a pub subsystem. You give it some set of actions, and it sort of distributes that to all of the people or all of the stores that are registered to listen to it. The only input for the store is the callback that it hands to the dispatcher when it registers. So what that means is the dispatcher will say, here's an action that has been taken in the system. And then the store sort of digests that action. And if anything has changed based on that action, then it will emit a change event for any of the views to check, to come back and check for new data. So the important thing here is that the only input to the store is the callback from the dispatcher. So its public interface only has getters. There's no setters at all. And the reason we do this is because having setters on the store sort of gives external control to anything that can call into the store. And that makes it harder to keep in a consistent state. It makes it harder for the store to sort of reason about what possible states it can be in. And if you ever debug sort of a hard to reproduce bug, it's usually because there's some sort of ordering of events that you didn't foresee, and it's hard to reproduce, and that's where Heisenbugs come from. So instead, what we do with stores is we say our only interface is sort of the actions that we'll accept from the dispatcher and getters for views to get data back out. There's no explicit setters. One way that I think about stores is as sort of a package of data and a sort of caretaker for that data. And the caretaker kind of observes a stream of actions coming in from either the user or the server or wherever, and it picks out actions from there that it's interested in. It might not be interested in all of them, but it sort of gets all of them. It has the opportunity to change its data as a result of that. All right, so Bill's going to go through an example app, and hopefully that'll demonstrate how stores fit in with the rest of the system and make all of this a little bit more concrete.
So yeah, as Jing was alluding to, this is where the stores get their data from the dispatcher. They register a callback with the dispatcher so that the data that's contained in the action can flow through the dispatcher and into the store. So the dispatcher really doesn't know anything about the store. All it really knows is that it has this callback that it needs to call at a specific time. Then the store will eventually, or the view actually will pull that data from the store into itself as well. The view at that point doesn't really know much about the internals of the store other than only the pieces that it's interested in. The store knows nothing about the view. So everything is very separated out and doesn't really touch each other very much at all. The store in particular is its own kind of universe, but let's talk about a little bit about how it gets the data into it. So like I said, the store registers a callback with the dispatcher, and we can take a look at what that looks like in some code right now. Here we go. This is the application that we're actually trying to build. This is the example application. It's basically kind of it's a simple chat. It's a lot like Facebook Messenger. And here in the application, if I can get mirroring going. I don't have my mouse. Okay, well, yeah, sure have. So, take this. Sorry. Okay, so what we'll see in the code is that we have a method on the dispatcher called register. That method has a singular argument, which is the callback. Thank you. And that callback has inside of it a large switch statement by which the store can decide and pivot on different things that it's coming in through that payload to what to do, and it can use the data that's in that payload to decide how it should update itself. And that's a really important point about about the store, is that it updates itself. No one updates it. It's a self-contained universe. for a logical domain. So here we are. This is how it registers itself, and this is the example of the switch statement. We can look at how we create a message here, and it's pivoting on the action type. You can pivot on other things, such as the payload source, but we often pivot on the action type. Then in this, we're creating some data around that text to create a message object. We're going to store that in a private hash that's inside that no one has access to. They can only get to it through the getters. And then we emit change. And stores are generally based on event emitter, node's event emitter, so that we can then event the change event, and the concerned views can pull the data from the stores. And I'll take questions at the end, okay? Oh, I'm sorry. Sorry about the washed out color on the screen. Maybe I can just make this bigger. A little bit better? So again, if we're creating a message here, we're doing this. We type in this into the view, and we'll talk about this in a second. That's going to wind up going into the payload and coming back in through the dispatcher into the store. So the controller views are the ones that are listening to that user event that I just did on the application. The controller views are just like any other React components, but they have this special job to do, and that is to listen to change events. And when they hear that a change event has happened from any store, they call the stores that they're interested in with the getters and pull that data into themselves. They then update their state and re-render all of their children with the new data. So let's take a look at what that looks like in code. So generally, so this is the message section. This is the entire area of the page that's about the message list there. And generally, these controller views will maybe control a section of the page and all of the children that are underneath them. So in their when they first initialize, they get their initial data from the stores, and that's a method up here where they're going to call one store to get all the messages for the current thread, and they'll call the thread store to get all the current messages, to get which thread is the current thread. As the lifecycle methods progress, here we have component did mount, that's after initialization. They set up their event listeners. We have onChange as our response to that event, and we call that same method to grab the data and update our state. So we get the data from the stores, and we call set state. And when you call set state in a React component, it sets off the rendering cycle. So then when we come up here to the render method, we have things like this .state, thread.name to pass down into the children. So, or in this case, we have a list of message items that we're mapping over the messages, and we have a little get message list item, and this is the child message list item, and that's our stateless React component. So let's go back to slides here. When the view actually responds to a UI event, it will, inside of its event handlers, want to call one of the action creator methods. Action creators are methods that wrap around the creation of an action and then pass that action to the dispatcher. So that's how the data comes back into the system and starts at the top and starts flowing back down again to eventually update the store. Just like views can create these actions, API interactions can create these actions as well. Actions are the entry point into the system for anything that needs to enter the system. So that could be initialization code, like when it first launches. That could be a call to the API and you're getting data back. That could be a user interaction. I'm thinking to myself, maybe that could be like, after some of the talks today, maybe that could be like a router change. So anything is going to create an action to get into the data system. We can also, in that same action creator, siphon off the data and do a write to the API. So we can exit the system as well through the action creator. So let's look at how we might add threads to our system. We've had a singular store, a message store, and a message view. We would simply create another store, a thread store, and a thread view. The difference here is that the message view is going to be listening to both stores because it needs to know both things. In our application, you can see that Bill and Brian is the thread name, and then we have a list of messages. This whole section is governed by the message section. This section over here is the thread section and is a different controller view. Eventually, we may add yet another store to track unread threads. Now, because we're storing whether or not a message has been read in the message itself, we need to know. We need to have reference to the messages, and the thread is already being known, is already a dependency of the message store. The thread store is something that the message store needs to know about. So we can't have a circular dependency occur. So we'd create a third store to manage the unread thread stores. And then all of these need to be kept in sync. And this is where the dispatcher really shines. The dispatcher has a special method called waitFor, where the stores inside their callbacks can declaratively say, I need to wait for this other store to update first. And thereby, everyone stays in sync in a very declarative model. So the unread thread store needs to wait for both of the other stores to update first before it can update itself, because it depends on some data that's in those stores. So that's waitFor. It allows us to sequence updates and allows us to set up a hierarchy of stores. For example, in our situation, the thread store has no dependencies. It's at the top of the hierarchy of the stores. The message store is a little bit below that because it needs to depend on that thread store to update first. The unread thread store is at the bottom there, waiting for everyone to finish first. But eventually they all they all emit a change, and the whole cycle updates. Now Jing's going to talk about where else we might go to evolve the app.
All right, great. Thanks, Bill. So, what I mentioned at the very beginning is that, we want to sort of keep a simple mental model so that as we sort of evolve the app, all of the things that we add in doesn't sort of explode the complexity and the number of things that you have to think about within the system, right? So let's look at a couple of examples, and I won't use code in this case, but hopefully it'll give you a picture of like where we'll slot in new stores and new features as we add to it. Oops, sorry. So let's say that we wanted to take this system and add the ability to start a new conversation, right? So this is a very common action. We don't want to send just a new message, but we also want to start a new thread along with that. So the action payload might look something like this. We give it a type new thread. And here it's like a little bit less structured than we would normally have it, but for the purposes of demoing, let's make it simple. So we'll just say this message is to Bill, and I'm going to use first names as IDs, just so we don't have to use numbers. And the text will just be, hey, Bill, I'm just talking to him. And this is going to be from the viewer, which is going to be me. And I'll assign a temporary thread ID and a message ID on the client, just so we have something to refer to it with. So how would the thread store react to this action? So the thread store internally has a map of threads right now, from the thread ID to an object with some metadata in it. So here, in this case, the thread store would look at that action with all of the metadata in it and sort of infer a couple of fields from it for the new thread that it's creating. So we know this 5E93696F thread has a couple of features. It has a participant list consisting of Bill and me, since I'm the viewer. And then we know that the first message on that list is going to be the temporary message ID that we created. And in this case, the message store is going to react in a very similar way. It knows that we've added a new message to the map. So we'll take that ID and we'll create an object that has the text of that message, the thread ID, so we know which parent it belongs to, and the author is me, and it's going to be the viewer. So what's important here is that, when you think about when an action comes into the system and you think about how it should affect the system, you can sort of zoom into a particular store and think about, okay, how does that affect the data within the store? You don't have to think about all of the other interactions with everything else in the system. You just think about the very simple, constrained problem of how should that affect my data. Let's take another example. Let's say we wanted to add a feature with group chat. So I want to be able to add a participant to a thread and remove a participant from a thread. So in this case, the action might look something like this. It has a type as well. We already know the thread ID because it exists. And I'm going to add a new participant with the unique ID Chris, and some metadata about that person, right? So that we can sort of render his information into the view. We need a profile picture and we need a full name, Christopher Chateau in this case. So it's pretty easy to see what the thread store will want to do. Given that the thread ID already exists in the map, we just want to update that map to add another participant to the list. But we don't want to sort of store all of the metadata for that participant inside of the thread store. That doesn't make too much sense, especially since you can have the same participant on multiple threads, and then you don't want to sort of get out of sync with all of the metadata about that participant. So instead, what we want to do is we want to add a third store, the participant store, that just keeps track of all of the people that we know about on the client. And when it sees this action, add to thread, what it does is it adds this new participant to its map, if it's not there already, and it creates some metadata about it, the name and the profile pic, right? So if we look at this system, what we end up with is 3 stores and 2 views, right? And Bill, at the end of his example, also had an unread thread count store, and a different view for that, right? So here, I'm not even showing the 4th store because that wouldn't even fit on my slide. So this gets pretty complicated, and you can sort of see how, as you add features here, you would add more stores or more views to sort of manage different domains. And hopefully the thread store versus the participant store gives you an example of when you would want to split off into a new store rather than keeping it all in the same place. But again, all of this gets sort of complicated, and we have all of these arrows going back and forth. Where is this scaling? Well, all of this basically reduces back down to this diagram, right? We want to be able to say, because all of the arrows flow in one direction, you can sort of collapse all of the stores into one piece of the system and all of the views into one piece of the system. And this is what it looks like when you sort of zoom out, when you think about how the data flow works in general, not in a specific case. And then while you're working on it and you want to sort of think about how a new action would fit in, or a new store or a new piece of data would fit in, then you can zoom into the stores at an individual level and think about that, right? So instead of having to hold a large system in your head and sort of all of the cascading changes that might happen within that system, you can sort of keep this in mind and then zoom into some particular pieces. And I think that's what we found has been really useful in just keeping the complexity low and making it easy to test, since you can test each individual store and how they react to different actions. And the other, I think that's it. So at this point, Bill's going to talk a little bit about how Flux fits into a broader picture.
So Flux is obviously somewhat influenced by MVC. But it's also influenced by a lot of other ideas, and it fits into this world that's a little bit bigger than just MVC. So these are some of the things that seem fairly similar to Flux to me. There's a lot of concepts here, like in data flow programming, for example. There is that concept of very distinct ways of getting in and out of the objects in the system. And the stores, reflect that in that they have that callback as a primary, the only way something can push into the store. Other than that, the store can pull from other stores, but other than that, it's the only way that something can push in. Likewise, the getters are the only way somebody can pull the data out, and the only thing the store is pushing out is the event. In addition, data flow programming has that concept of waiting for the inputs to become valid, which is similar to what's going on with wait for. In CQRS, that's stands for a command query responsibility segregation, I think. It's actually a very similar pattern to Flux in that the action, in a way, is the command cycle, and the controller view asking for the data from the store is like the query cycle. In CQRS, those are both models, so it doesn't exactly map to Flux, but there is a certain similarity there, and it's certainly a one-directional data flow. In functional programming, there is that emphasis on a unidirectional data flow as well, as things flow through functions. And in pure functions, and that's somewhat like what React strives to do. You can think of a React component as being a pure function, ideally, where the data is flowing through the system, very similar to the way it might flow through something in like Haskell. So those are the other things that we think that Flux is related to, even though it is obviously somewhat related to MVC as well. And I think that it's appropriate to think of it as being influenced by probably a lot of different things. So let's talk about where we're going. We have an open source dispatcher today in the new repo, and this is the same dispatcher that we use at Facebook. And it includes wait for, and in addition, and it will fire off an invariant error if you create a circular dependency. So it's a very robust dispatcher, and we use this in production all the time. That's been something that those people that have started to become interested in Flux have been waiting for, and so we're very excited today to release it. We also have the example chat app that I briefly showed on the screen, and you can take a look at that. And we also have an example, a to-do MVC app, but the to-do MVC is somewhat simplistic, and this new chat app shows a little bit more complexity. So it's like a good second step as you learn about Flux. And in the future, what we're thinking about is perhaps some Flux boilerplate code or some CLI tools to get you quickly up and running, because there can be a bit of code to write at the beginning, which can slow you down a little bit. So we want to make things that can help you get a little bit faster. What we do need, though, if anybody's interested in open source projects, are utilities to plug into your favorite whatevers. And in particular, there isn't a really Flux-oriented router in the world right now. And that would be a great project for someone to take on. There are a React router, but it's not done in a Flux kind of a way, where it creates an action. There's more Flux stuff. If you get the slides, you can get these links. But there's documentation on the React blog. There is the to-do MVC is accompanied by its own tutorial. And there are some new screencasts from Egghead about Flux. And someone has created this thing called Fluxor, which is like a set of tools for getting going with Flux that they wrote in response to the to-do MVC example. So that's it for us today. Thank you very much for taking a listen at how we build web applications at Facebook. Any questions? How do you populate the data server side?
Exactly.
You mean how does it come into what makes it an action?
No,
What calls the API?
No, in your component, you say,
go ahead.
hey, my component called the store to get the data, right? But in the server side,
You're asking how we get data into the system in the first place?
no, not in the first place, but
Okay.
when I transfer, so the component should be fast.
Yeah, so there's sort of two parts to the question there. One is how do we get data sort of onto the client from the server? Is that correct? So the way we normally do that is we still have everything coming into the dispatcher. So from the server, we'll sort of send a payload down that's meant for the dispatcher that says, here's all of your initial data. And then the other side is like, if your view asks for some data that we don't have on the client, how do we get that? And the way we do that is when you ask the store for data, very often we will give you a callback instead of returning your data immediately. So your view sort of has to deal with that interaction where the store may not have the data that you want on the client. And in that case, the store is responsible for sort of fetching data from the server. But the one distinction there that I should make clear is the store doesn't take the response and only like consume it by itself. All of the stores sort of take the response from the server and redirect it through the dispatcher so that everyone can sort of look at that initial data payload and modify their own data if it needs to be. But in general, like we think of data loading or requesting data from the stores as asynchronous operation, possibly. So we try to leave that possibility open. Is that?
And also, we typically create like a web API utilities file. When we don't actually handle the calling of the server and that sort of stuff directly in the store. We usually just expose that to the store, and the store can use those utility methods.
Do you have a follow-up question?
I had a quick question about what you just said, where you said that the store would go across. So does it create an action that goes all the way back to the top and then funnel down to the dispatcher?
Yeah, so we sort of think of that as like, when the view has a sort of the beginning of a flow is starting with an action, right? So when the view asks the store for something and it doesn't have it yet, that's sort of the read path rather than the write path. And so that hasn't even started going into the right path yet. Instead, when the store goes to the server and asks for it, and when it responds, that's the beginning of sort of the update flow of like, when we're going down through the center. Did I forget to repeat the question?
I mean, to be honest, most of the time when you're asking for data from the server, you're doing it in response to a user action, and so most of the time that utility method is actually going to be called in that action creator, that the same type of action creator that the view would use when you like hit enter, right?
Okay, so the question is, how do we go around enforcing the constraints? That's a good question. I think a lot of it is going to come down to culture to some extent within a team. Once the system is set up so that your stores don't have any getters, your stores don't have any setters, and everything comes in through the dispatcher, it becomes really hard to do it any other way by modifying just pieces. And they sort of, the developer kind of feels gross while they're doing it. So I think this is kind of like a pit of success thing, right? You want to make it easy for them to do the right thing and want them to make it hard to do the wrong thing and make it feel kind of weird in the first place. So I don't have a great answer there, but a lot of the enforcement is going to come down to just having example code there and good unit tests. And
I think part of the strength also is the simplicity of the model and how quickly developers can learn it and get ramped up on it. It's something that the team can share a common mental model really easily.
Yeah, so the question was, do we use anything with Socket.io instead of just async endpoints? Is that right? I don't believe we've done anything in particular with Socket.io, but it sounds like we have something similar, which is what we use for chat updates. We have an open channel that uses Longpole on Facebook, and that's how we sort of get updates pushed from the server of, somebody new commented or somebody sent you a message. And for those, we sort of just like subscribe to the channel and dump everything into the dispatcher. So, the nice thing there is you can treat a payload coming in from the channel the same way that you would treat a payload confirming that you sent a message, or, an optimistic payload that, you're sending a message on the client. So that actually simplifies the paths a little bit. So the question is, how do we deal with hooking up the UI to the actual actions themselves? A large part of that is going to be, or at least we handle it within React. So you can set sort of click handlers, drag handlers, things like that from a React component. And then, when we're rendering our React component, we just hook it up to the action creators that say, handle a new message with this text, or handle that somebody clicked a like. Does that make sense?
Think about that. One thing that's really nice about React is that it automatically does event delegation for you. So you can feel free to like add these handlers on every single list item. And in reality, what's happening is at the top level, there's like one event handler going on. Yeah.
Other questions?
That's exactly right, and that's why we included that error message in the console in the development environment. Like, so if you're in development, you will get an error if you create that situation in your browser console. But yeah, that is definitely a problem to avoid.
So just to clarify one thing, the wait for isn't sort of global. It's actually, we mostly do it per action type. So you might have the messages store depend on or want to wait for the thread store for one action, and then you can still have the opposite relationship as long as it's a different action. So it's not a circular dependency if that's the case. Other questions? Seems like that's it.
Yeah. Thanks very much.
All right.
Everybody.
Thanks.
Really appreciate it.